guy out of the way. Sorry, I'm going to be looking away from you because I've got my slides coming up on a different screen here. So we're going to still consider the full energy equation. We went from derivation last Thursday, a little bit of application yesterday during the recitation, and then today we'll do some more application as we learn to use this full equation. Announcements, remember there's a new extra credit opportunity. It's due next Thursday at either 5 p.m. or midnight, something like that. The final will be held on Sunday, May 2nd from 4:30 to 7 p.m. And the next to last homework is due today. The final homework will be due next Thursday as well. I guess let me pause for a second and ask if there are any questions, and then I've got one more business thing to talk about.
I had a question real quick. So homework 11, that consists of 2 separate problems in the Wiley again, correct?
2 separate problems. Three pieces, right? So there's part 1, part 2, part 3. So 2 written and 1 Wiley. Is that what you mean?
Yes, that's what I mean.
Yep. Yeah. So are you having trouble seeing those at all for some reason?
No, I was just checking to make sure. I haven't looked for homework 11 yet.
Oh, okay. Perfect. Yeah. Just let me know. I goofed up somebody, just the mechanics. I don't want to get into the details of how Canvas works, but somebody had asked me for a change of date with something they had to do on homework 10. And I accidentally made the change to homework 11. I don't think that should have affected everyone, but in case it did, just let me know and I can go back and check it. But I think I made that one clean. I think that's okay. But yeah, let me know if you have any problems. Alexi, did anything else pop up?
Yeah, someone just mentioned, I assume you just misspoke when the homework this week, homework 10 is due on Thursday, not today.
Sorry. Of course on Thursday. Maybe I jumped forward in time. Sorry about that. Yeah, homework, it's 11 though, right? It's 11 that's due on Thursday, not 10. 10 was last week.
Oh, yeah.
Yeah, okay. Great. All right, we'll between the two of us, we'll get our story straight here. So, okay. Yeah.
They printed out the notes at the beginning, of the year, but they end. They seem to. There's not any stuff about Buckingham Pi and
right. So I put some notes together last night for dimensional analysis of Buckingham Pi. I haven't posted them yet, but I'll get them posted today after class. I should be able to remember to do that. So those will be ready for you and they're a little more kind of straightforward, fill in the blank kind of thing for Thursday and Tuesday. So yeah, you'll see those tonight. Yeah, thanks for that. Okay. One additional thing. So we, Alexi, Emma, and I are fully aware that Chegg exists, and there are probably other resources like this out in the world. And there are at least 2 ways to use resources like this. One is to reinforce your learning somehow, but the other one, of course, is to blatantly take the solutions that are provided to problems like the ones that we use in this class and blatantly write down exactly what is provided in these online forums or online resources. And sometimes this is obvious because there are mistakes that are made in the Chegg solutions that people repeat in their own solutions. So throughout this semester, we have caught a few of these, and I have reached out to you, and I appreciate, I'm not going to name names, but I want to just speak to you and say I appreciate that when I reached out to you and said, this is a problem, that you met with me and we talked through this process, and I did not go further with respect to reporting to the academic honor office. However, all of you signed the pledge at the beginning of the semester. Homework 0 was basically accepting the honor code for the university, and it said that you would not do this. So some of you are probably going to get an email from me later today because we found a bit of this problem on homework 10, which we'll get grades posted tonight. They're just about finished. I mean, obviously the Wiley part, you guys get the instantaneous email or gets posted right away. For parts 2 and 3 that are written, we have to hand grade those. And we'll get those posted later tonight after I send out those emails. For the next two homeworks, 11 and 12, we are on the hunt for this. We know that when we start looking at your process and it seems really strange, why would you do it this way? That's usually an indicator, a red flag that we need to go look for a different resource. And sure enough, it often turns out that the same wrong approach or strange approach is being used somewhere else that we can find on the internet. So that is academic dishonesty. You will not receive a grade for that, and you may be reported to the Honor Code Office, which is what we all agreed to at the beginning of the semester. So I'm just letting you know that we are not immune to understanding what's out there, and we are on the lookout for that to make sure that everybody is providing the work that they actually did. So just as a heads up. So for homeworks 11 and 12, please present your own work as you try to learn these concepts and take them forward with you, because learning how to just pull off a cheg is not going to help you when you've got to design a culvert or whatever you're going to do in your professional life. Rarely are the templates out there for solving the exact problem that you have. So just a heads up. All right. I hate having that conversation, but it is necessary. Okay. This is just going back to a slide that we had filled in on the last Thursday, so don't feel like you have to write this out. This and the next slide will actually be review. So we had this full expression, and again, I apologize for not having my writing tablet. Like, I'm just sort of caught off guard here. So you're going to see a lot of animations here today. But this was our full energy equation. And we basically said that this is the change in time of energy stored in the control volume plus any flux of energy out minus the sum of any energy inputs to our control volume or through control surface equals, and now we've said that we have some change potentially in our internal energy plus some possible change that's added to the control volume from work, some power that's added. We usually call that shaft power, right? And so this is set up as a sort of a positive to be an input in this case. So this net in is right here, and this dot over the W and the Q indicate rates. Okay, so time rates. So we've got W is actually can be broken up. This work can be broken up into shaft work and pressure work, where the pressure is in components of this P times V times A, right? So that this is one way in which we have sort of non-shaft power being applied to our system or to our control volume, essentially. And so we can look at the ins minus the outs on this with respect to that component right there, or we can just focus on the shaft component of this. And so yesterday in recitation, what I tried to get across was this notion that the shaft part, we can, try to come up with like horsepower, for example. And then we also noted that there's this total energy, which is equal to some internal energy plus kinetic energy plus our potential energy here. So this looks a lot like what we had previously in the Bernoulli equation, slightly different here. This is put in energy units. So it looks a little bit different, but it's more or less the same representative components. When we put all this together, the very long equation is this component of the stored energy changed through time, integrated over the entire volume, plus the fluxes of energy, total energy. So all, in this case, these are four components because we're also including this pressure piece right here. So pressure over rho. So this is the sort of work plus kinetic plus internal plus potential. All of that multiplied by rho out, V out, A out. We can subtract the summation of all of the inputs as well. And all of that is equal to then the Q and the shaft component. So what we've done with this net, broken it up into shaft and pressure, the shaft stays on the right, the pressure component got thrown into the fluxes across the control surface, okay? And then finally, if we have steady and incompressible one-dimensional problems, we break this down to something that looks like this, where the total energy change with time is not is zero, right, internally. And so we're just looking at the input fluxes, including whatever input of shaft work is occurring, is equal to the output fluxes plus any change in these losses of energy. So any output of our internal energy minus the heat change in some case, like if we were cooling as we went from location 1 to location 2. Okay, so this is the way we're setting up this energy approach, is to use, think about all the energies at one location plus whatever can be added or subtracted before you get to the other location. So this is Bernoulli sort of on steroids, where we have to include a few additional components. All right. So I'm going to take you through 4 problems. 3 of them are directly from your text. One of them is from the back of the chapter. And we have 2 on pumps and 2 on turbines. So the idea is, let's first look directly at what happens with a pump and just right across the pump. And then we're going to zoom back out to a pump within a system, like pumping water between 2 reservoirs. And then we'll zoom in on a turbine and then zoom out to look at what happens with a turbine in, again, a broader system of energy. So at this first point, then, just starting to look at the pump energy change across the pump itself, we can see that the inflow side here has a diameter of 3.5 inches. The outflow side has a diameter of 1 inch. And there's a pressure of 60 psi on the downstream end, 18 psi on the upstream end, and a flow rate of 300 gallons per minute. Now that's only noted on the outflow, but of course there are no other pipes shown to be input here, so that Q is also going to apply to the upstream side as well, right? The pump is not removing water, it's not adding water, so whatever this flow rate is on the outlet side has to be valid for the inlet side as well. So a pump delivers water at a steady rate of 300 gallons per minute, as shown in this figure. Just upstream of the pump, where the pipe diameter is 3.5 inches, the pressure is 18 psi. Okay, so we have a P1. We have we can calculate a V1, right? We can say Q is equal to A times V, solve for a V on this upstream end, and we should be able to start to populate essentially some version of this equation, okay? And in this case, we're not gonna worry about this component of heat. I'll tell you why in a moment, but we do wanna get at this shaft component here, we expect. All right, just downstream of the pump, where the pipe diameter is 1 inch, the pressure is 60 psi. The change in water elevation across the pump is 0. Okay, so our Z's, the potential energy, there's no change in potential energy. So that difference can be left out of our equation. And, oops, that should be I'm pretty sure the rise in internal energy associated with a temperature rise. So this, I couldn't find a way to get these little upside down hats in, like we have here. These little guys, but these little chevron things. So that's what should be here. So this U2 minus U1 we're given is 93 foot-pounds per pound mass. All right, so that we can put in. And then it says here the flow is adiabatic. And when we say adiabatic, essentially what we mean is that there is not, so we've been told that there is a temperature change here, but we're not, that's an internal one. And this would be an external one that is occurring from one location to another. So when we use the term adiabatic, essentially it means that this term goes away. I'll show you that on the next slide. So determine the power in horsepower then required by the pump. In other words, we're given enough information to calculate the energy on the upstream end of the pump. We can calculate all the components of energy on the downstream end of the pump. And the question is, how much horsepower is required by the pump to make that energy on the outside occur given the incoming energy on the upstream side. All right. So the first thing we want to do is, sorry, that should have come in. You can ignore this for a second. That didn't make my animations very well, apparently. But let's start with this top equation. So another version of the equation we looked at 2 slides ago shows an m dot out front multiplied by this U hat out minus U hat in. So that's that temperature change, sort of internal energy, plus P over rho out minus P over rho in, plus then our difference in velocity or kinetic energy components, plus this difference in the potential energy is equal to Q dot net in, W dot shaft net in as well. Now, the simplifications from what we read in the previous, the problem statement indicate there's no change in elevation. So Z out minus Z in is equal to 0. And we're told that the flow is adiabatic, which means that this Q net in is also equal to 0. Sorry, I should have had a dot on top of that, but that's another thing I haven't quite figured out in PowerPoint, is how to get that on there without creating an equation. So from this, we can cancel out the Z out minus Z in, right? That there is no change there. So that sum is going to equal 0. Or rather, that difference. We said it's adiabatic, so this Q net goes away as well. All right. Now, we're going to need out, and we were given that this was 93 pounds mass feet per pound, something like that. We were given that difference here, right, in the problem statement. And we were given these pressures, an out pressure and an in pressure, and we can calculate the velocity. So let's start with just M dot. We're going to need that out front here. What is our mass flow rate through this system? So, of course, M dot is equal to rho times Q. Rho is 1.94 slugs per cubic foot. I would never write this as a force per, like a pounds per cubic foot, by the way. In the back of your book, it's always written as slugs per cubic foot. So, just a heads up. Multiplied by Q, and in this case, Q is 300 gallons per minute, so we have to do a couple of conversions. One is the conversion to convert this from gallons per minute to cubic feet per second. So those are in the denominator here. And then all we've done here is multiply by 32.2, ultimately pounds mass per slug, to get this into 41.8 pounds mass per second. We could have also reported it as something like, 1.3 or so would probably be slugs per second if we had written it that way. That would have been okay as well. But one way or another, we've got this mass now. This mass flow rate. It's either in pounds mass per second or in slugs per second. All right. So that gives us this. We were given these two. We've got that. We've got this. We need to calculate our V's now. So what is V1 and V2? All right. We need the V's for the energy equation. So we can go back to our good old friend, the continuity equation. We rearrange it to solve for V. V is equal to Q over A. A is circular, so pi over 4 D squared is what we put in the denominator. And ultimately for V1, what that gives us is 300 gallons per minute times 4. So that's just this 4 from the 4 from the denominator here coming up to the numerator, or the denominator of the denominator. So that 4 is up there, and then we convert inches to feet, and we square that, and down for the D squared here, which is 3.5 inches. We've got pi in the denominator, and then we have our conversions from gallons to cubic feet and 60 seconds to a minute to get the flow rate into the right units. And when you go through that math, you end up with 10.0 feet per second. Okay, so on the upstream end, we're flowing at 10 feet per second, and we're going to assume it's uniform across the cross section. This is at least the mean velocity, right, when we use the continuity equation. V2, we can also calculate, again, Q over A2 in this case. So Q, again, 300 gallons per minute times 4 from our pi over 4 D squared in the denominator. The 12 inches per foot quantity squared is from converting this 1 inch diameter and squaring it, right? And then our unit conversion again for flow, we end up with 123 feet per second. Okay, so we go from 10 feet per second on the inflow to 123 feet per second on the outflow. And that's just continuity equation. The energy has not come into this yet. We haven't assessed energy. To get, regardless of what happens with the energy, there's no place to store this water. Okay, so whatever comes in on the inlet side to the pump has to go out on the outlet side. I'll take a sip while you guys are make sure to capture all that. Oh, and I was looking around kind of goofily for this quantity. Here's that U2 minus U1 equals 93 foot-pounds per pound mass. So in a way, this kind of dictates why we needed to come up with pounds mass here, because we ended up with this guy in pounds mass form. All right. So we're going to keep that same header here. Now we're basically just solving this equation for the shaft work. Okay, so let me walk through this. The first part of this 41.8, that's the M dot that we had already calculated, right? So that guy is there. But this 93, that of course is, oh, whoa. Okay, sorry. I don't know what happened there. Sorry, I don't want to make you sick here. This is where we were. Okay. All right. So that 93 foot-pounds per pound mass is U out minus U in. And then, of course, we have these P's set up, P over rho terms, right? That's this whole thing here. There's the plus term on the outlet side, the minus term on the inlet side. All of that other stuff is just changing the units from pounds per square inch to a force per square foot, right? And so we do this in two ways. The two steps are, one, we've got the conversion of square inches to square feet here. And then the second part is PSI, then we divide by the density of water and the acceleration due to gravity to get this into pounds mass, okay, from pounds of force. And then same thing with the inlet side. We've got, we subtract 18 PSI, convert that from per square inches to per square foot, and we divide by the density of water, and in this case, G, to get it into pounds mass instead of just slugs. And then the last term we have in here is the difference of the kinetic energy. So that's V out squared minus V in squared over 2. And we calculated these right on the previous slide. So there's 123 foot per second out. We square that minus 10 foot per second quantity squared, which is our V in. And then we divide by 2. And then once again, we're just making this conversion from essentially to get this into pounds mass, which is what we need in the end. And then we just make one last conversion here. Rather than displaying this in foot-pounds per pound mass, we convert to horsepower. Okay, so that is the last bit here, is just converting that into horsepower. And we end up with 32.2 horsepower, which is our final answer in this case. So what energy needed to be added by the pump to get the total energy on the output side, given everything coming in? We basically worked through this full equation up here to figure out what this value had to be, because without it, there would have been a difference. This would have come up with, well, I mean, it is the value that is the difference between the total input energy input and the total energy output. We have a mismatch there if we don't account for the pump providing something to give us the energy on the output side. That's ultimately how this works. Okay? Any questions on that? Okay. Let's go through one more here. Okay, so this was one that this is the image that I have, I think, on the cover slide for this equation, or for this set of slides. The pump shown in the figure adds 10 horsepower. Okay, now we're given an energy, right, a power that we can put into the equation. So we're given that the pump is adding 10 horsepower to the water as it pumps water from the lower lake to the upper lake, and the elevation difference between them is 30 feet. Okay, so find A, what is the flow rate, and B, the power loss associated with this flow. All right, so a couple of things here. Number one, we have no information. If you look at this image and you look at what we've been given, we have no information about a Q, an A. What are we going to do? Ultimately, what matters here is that we can go back to the energy equation and we have velocity included there. We're going to assume, because we're not told otherwise, that the diameter of the pipe coming into the pump is equal to the diameter of the pump of the pipe going out of the pump, right? So whatever velocity we have coming in has to equal the velocity going out. Okay, so it's going to be the flow rate in this case, whether we're looking at a Q or a V. We're not given an A, so I guess we ultimately have to look for a Q. We have to figure out some way of working through our energy approach to figure out where a Q will be. And the hint comes here in this 10 horsepower bit that we're given that W, capital W dot shaft value for energy. And then part B, the power loss associated with this flow, all right? So let's start with part A first. If we work with the head version of our energy equation, so this looks like the extended Bernoulli's essentially. So we've got the energy at the output side at 2 is equal to the total energy at 1 plus any shaft head that's added minus any head loss, any energy that's lost due to friction or things like that. Now, we're going to simplify this a little bit. We know that if we go from the top surface of this reservoir to the top of this reservoir, and you can see the way our control volume is drawn, that's not an unreasonable thing to do. P2 and P1 are both equal to 0, so those two are going to go away. That'll simplify things. And we note that V1 at this location and V2 at this surface are also expected to be 0. Okay, so, this doesn't feel really good perhaps because I've just simplified this so much. Where are we going to get a Q from? All right, first of all, let's distill this full energy equation to what we already know. Once we put in all of the zeros, we end up with H sub S, this shaft head, is equal to any energy loss plus Z2 minus Z1. Now, real quick, I just want to go back to the problem statement for just a moment. So I apologize, it's going to be a little bit quick. There's a question here about the power loss associated with this flow. What we really mean is we want to calculate H sub L, okay? So we're given that there are 10 horsepower of energy added. That is going to tell us, we could convert that to a shaft head. But there's going to be some loss that also occurs. And then we already know that Z2 minus Z1 is equal to 30 feet. So we have one equation and sort of two unknowns. What we're going to do is ultimately take this shaft head and look at how it is calculated in a slightly different way to predict what value it will be so that we can eventually come back to this head loss. But remember, the first thing we're asked for is the flow rate, right? So Z2 is equal to 30 feet. Z1 is equal to 0, and HL, the head loss is 15 feet. Were we given that and I just overlooked it? Nope, I think I'm revealing that a little too early. So my apologies there. Sorry, you can ignore this for just a second here, but for the moment, what we can do is take HS and we know that W dot shaft net in is equal to HS times gamma times Q. So that was a relationship. That Q is flow rate, and that gamma is, of course, the specific weight of water, or whatever your fluid is, in this case, water. That was an equation we wrote on Thursday that we're going to bring back because we are given that we have 10 horsepower that's of energy put in by the shaft, in this case, the pump. We can convert that into foot-pounds per second, all right? So we can make that conversion, and then we can divide by gamma and Q. And so in this case, HS is equal to 88.1 divided by Q. All right, now, let's see. So now the next step when we're looking at this is, I'm just wondering if I goofed this up and in my furious cutting and pasting to try to make these slides today, I goofed up where H sub L should have come in. I wonder if that was, I don't think it was given in the figure, but okay, HS, then our shaft head is equal to, yeah, somehow this is defined. So I apologize. It looks like I should have defined this in the problem statement, and for some reason I didn't. I can't pull it up right now, but my apologies. So this H sub L is a value that seems to have been given that we have here. So H sub S, our shaft head, we were given is 88.1 divided by Q from this relationship. We plug that in. If we know that our head loss is 15 feet, we add our difference in head for our potential energy, Z2 minus Z1 is 30 feet. Then ultimately, Q is equal to 1.96 cubic feet per second. So there's our first answer to part A.
I have a question.
Yeah.
I guess I'm a little confused as to what the shaft head is, to be honest.
Okay.
If you could explain that a little more.
Sure. So we were given that this pump is operating at 10 horsepower of energy, right? And so what we've simply said is that is work that is being put in, right? If we had this setup with no pump in here, water would likely go out of reservoir 2 and flow into reservoir 1, right? Without some kind of barrier in here. But to move water from 1 to 2, we need a pump that is going to push water. It's going to add energy, right? And the energy it has to add has to overcome this 30 feet of potential energy difference. So telling us for the problem statement to tell us that we have a 10 horsepower pump that's going to do this, that essentially says that's how much power I have added just in different units, in the units of horsepower. We can't just plug horsepower in here. We need to modify that to basically get it into the right units, to put it in head units here. Does that help a little bit, Amara?
Yeah, I think so. So I feel in other problems we've done head pump, the pump head.
I don't think we did many of those yesterday, but ultimately what we did yesterday was, one case I think we looked at whether we ended up with a turbine or not for the shaft head. So it's more formal, I guess I would say, to just call H sub S the shaft head. And if you find out that it's positive, then you have added energy to the system, meaning that you have a pump. If it's negative, you've taken energy out of the system, and that means that you have a turbine. So that just, rather than, if you call it H sub P, you sort of assume it's a pump, and when you find out it's a turbine, you're like, oh, it's an anti-pump or something like that, right? And so H sub S just makes it a little more general. Does that help a little bit in translating?
Yeah, that definitely helps. Thank you.
Okay, sure.
One question.
Yeah.
So I think in a problem yesterday or in office hours, we had the H sub S on the other side of the equation. How do we know which side it goes on?
So that's a good question, Elizabeth. In general, when we boil it down to this version of the equation, note that this would have been, all the ones would have been an inflow, right? If we put it on the left-hand side, if we moved all the P1, P1 over gamma, V1 squared over 2G, and Z1 to the left-hand side, they would all be negative, right? And that negative is, oh, sorry, I realize this is a little ugly. That negative is essentially putting it on the left-hand side of having Q and W shaft on this side. So this is like an H sub L, and this, I guess it doesn't have the negative in front of it, but this is some way of having an energy exchange. This is that shaft component that we can convert to an H sub S. All right. So in other words, let's see, where were we? I think we were here. We had gotten to that value there. So all of this is sort of saying like, this is my outflow. All right. So at point number 2, at some location number 2 at a downstream location, I have started at an upstream location with all of this energy, and then I may have added some from a pump, or I may have, this could be negative, right? I may have removed some because of a turbine. and it may have also had some losses because of friction or other things, or maybe there were some valves in there or bends and so forth. And so ultimately what we say is that the energy at the end of this whatever sort of a coupled, I'm going to call this, I don't want to confuse, I don't know another word than system to use, but I want to be careful that I'm not talking about the fluid system, right? The system of reservoirs and pipes and pumps. In this case, we're saying that the energy that's at 2 is equal to the total energy at 1 plus whatever energy has gone in due to a shaft minus any losses along the way. Does that help a little bit, Elizabeth?
Yeah, so what you're saying is we just kind of have to think about the given situation and like where it makes sense for it to go.
Yeah. Now, the reason that in the other version of the equation where you see shaft net in is because that means that in general, you are the plus when that is a plus sign, when that is a positive value in the equation, that means that you have added energy to the system. Okay, like as a pump. And so if it comes out to be negative, then so be it. That's fine. You've taken energy out, and that's okay through some kind of shaft work like a turbine.
Okay.
Okay. So what about the power lost associated with this flow? So remember, head loss was equal to 15 feet. Did I miss something where that should have come out real obvious? No, I don't. I must have missed it in the given, so my apologies for that. Anyway, the head loss was equal to 15 feet, and we can rewrite this equation that we saw just a moment ago, where we figured out Q on the previous problem as being W dot divided by, we were looking for what was it? It was we're looking for H sub S and W dot in that case. So, okay, so in this case now, all we're doing is taking that head loss term, the H sub L, and we're just converting it to a power. Okay, so how much power is lost given that we have a head loss of 15 feet? So all we're doing is converting this from a head to a power value. And the way we do that is by multiplying by Q, what's our flow rate, and multiply by gamma, our specific weight of water, right? And so we can plug in 62.4, right? That's our specific weight of water. The flow rate is what we calculated in part A. And we were given that this head loss is equal to 15 feet. And so when we multiply those together, we end up with 1,830 foot-pounds per second. If we convert that to 1 horsepower, then we basically end up with the 15 feet of loss that we were given, that the head loss that occurs as we go through this bend and along these pipes and so forth, ends up being the equivalent of 3.33 horsepower. So real quick, I just want to go, well, maybe I can read it. We were given that this was a 10 horsepower pump. And then we also had 15 feet of head loss occurring. Really, all we need to move the water from section 1 to section 2, assuming that we had no losses in between, is 10 minus 3.33. So 6.67 is all we really need. But because there are losses along the way, because there's some friction of the water interacting with the pipes, because there might be valves or whatever, we need the 6.67 plus 3.33 to ultimately get water all the way from reservoir number 1 to reservoir number 2. All right. Any questions on that? Oh, sorry. Sorry. I didn't box it, but that's the total value there. The final value, the final answer.
Sorry,
Can you go
but
back a slide just quickly.
Sorry, one more time.
Can you go back a slide quickly?
Oh, sure.
Thank you.
Was there another question in there? Okay. Okay. Was that long enough? Ava, did that work for you?
Yeah, all good. Thanks.
Okay, perfect. Okay, so now what I'd like to do is just take our 10-minute break to work to give you guys an opportunity to work through the FCQs. I guess I could have put on some music. I didn't think about that. But I'm just going to go ahead and mute myself, turn off my camera, and I'll wait until, so it's now 13:30 on my my clock on my computer. I'll wait until 13:40 and get started again. We may not make it through both of the next problems, but at least if we get through one more and then get to the participation question at the end, we should be in good shape. So I'll stop talking and give you guys a moment to fill those out. I know they've changed format. I guess that started last fall. And there are some new opportunities in there to kind of provide feedback on other things. But and some of those probably I don't do very well. For example, talking about like diversity and so forth with respect to fluid mechanics. Fluid mechanics are mechanics, but I actually have I've been thinking about some ways to do that. So in the future, this class might change a little bit, but for now, I guess we're sort of hitting the fundamentals of fluid mechanics as best we can. In any event, what I'd like to do now is go ahead and shift gears and try to get through these next two problems. We'll see how well we do at that before the end of the period. I will, if we run out of time after this next one, I'll jump ahead to the participation question to make sure we get it in before the top of the hour. At the top of the hour, I do need to jump to a fairly important meeting with respect to Instar, my research institute here. So I want to try to wrap up at least a little bit before 2. All right. Thanks very much for putting effort into to the FCQs. I mean, we take feedback seriously and think carefully about how we can improve our classes. So, all right. So now like we zoomed in on a pump, let's zoom in on a turbine here. And now we're going to look at, there's some steam turbine here. It's a little bit, there's a picture there in the top right, but what we see in the lower right is some very simple schematic of it. And what we're given here is a velocity and an enthalpy in this case. On the upstream side, I'll define that on the next slide here in just a moment, but it's essentially a energy per unit mass. And at the outlet side, we also have a velocity and an enthalpy. So a steam turbine generator unit used to produce electricity is shown in the figure. Assume the steam enters a turbine with a velocity of 30 meters per second and an enthalpy of 3,348 kilojoules per kilogram. The steam leaves as a mixture of vapor and liquid, having a velocity of 60 meters per second and an enthalpy of 2,550 kilojoules per kilogram. Okay, so One thing to note, enthalpy is of course an energy term. We've reduced our energy by 800 about, maybe it's 798 or something, kilojoules per kilogram. Okay, so just keep that in mind. The flow through the turbine is adiabatic, so that means our Q, capital Q dot on the right-hand side of the equation will be 0, and the changes in elevation are negligible. Okay, so our potential energy doesn't change, right? That Z in minus Z out term on the left-hand side, or Z out minus Z in, would be negligible as well. So what we're asked to determine here is find the work output involved per unit mass of, that should be steam through flow, not stream through flow. I write stream too often, apologies. So that should be steam. All right, so on the outlet side, so we've got some flow rate. Now, if we want to calculate M dot, note that regardless of whether we're talking about steam or liquid water, whatever comes in as steam is the same mass per second going out on the other end, even if it changes its phase a little bit, right? We might try to modify that if we had a flow rate of the liquid water versus the steam and so forth. For now, we assume that there's really nowhere to store liquid water. It's all got to go out, even if it changes its phase a bit. Okay, so whatever comes in as steam, whatever mass per second that is, has to go out in mass per second on the other end. All right, so now we've got a slightly different version of the energy equation. This one comes from your book as well. M dot multiplied by, now we've replaced those internal energies with enthalpies here. So, and again, I'll define that in just a second. I have a formal definition. And then, so we have out minus in plus the difference in out minus in of our kinetic energy plus our out minus in difference in potential energy. And again, this is going to go to 0 because there's no change in elevation. We were told it's adiabatic, so this term will go to 0. And the question is, how much, let me get the right words here. The work output involved per unit mass. And so what we're looking for is essentially a W dot shaft. We're going to need to put that in the right units because it's said that it is per unit mass. But the idea is that we're solving for W dot here. All right. Enthalpy is basically the total heat content of a system. So that's going to be its internal energy and its temperature as well, the thermal component. So it's total heat energy. Total heat energy content of the system. So this is just the not the internal energy as much as just the heat content. So how many joules are there essentially? And there's no change in elevation, so we can cancel that out. And we said it's adiabatic, so we can cancel that out as well. All right, so we are given these two values. We should be able to back out. Oh, we're given V1 and a V2, so a V in essentially and a V out. And we can solve for this W dot value here in a second. The way we're going to do this, though, is slightly modify it because we're asked for a different sense of units. In this case, we'll be looking for this little lowercase w. So lowercase w, the shaft net in work per unit mass is W dot divided by M dot. Okay, so this capital W dot divided by M dot. All right, and so what we need to do then is basically we can solve for this. All of this actually falls out of this equation, right? This, if we bring the M dot over and divide by that, then we're just left with this H hat 2 minus H hat 1. So we've replaced out and in with 1 and 2 here. I don't know why, apologies for this, but for some reason the V changed. This is V2 out, the velocity on the outlet side, minus V1 squared, and that's the inlet velocity there. It shouldn't have changed to a lowercase value, but in any event, that is V1 and this is V2 as given. And we also note that this is set up with a sign convention of the if it's positive, then that is an input of energy like a pump. When we're looking at the net output, because we know it's a turbine, Then we would say it's just the negative of the input, the shaft input. Okay, so we can just reverse the sign. So essentially, we could go through and reverse the signs here to figure out how much energy is being given off little W shaft by the steam turbine. Okay, so we can basically take this and reframe it now. So when we put it into net output, we just multiply through by a negative. So now we have H hat 1 minus H hat 2 plus V1 squared minus, again, this should be a capital V2 squared, but all we did was change the order of these, right? If we multiply through by a negative, we get V1 squared minus V2 squared over 2. So we can plug into this. We have the 3348 on the inlet side minus 2550 on the outlet side, plus, and then we have to basically, we have our two velocities here. The inlet side is 30 meters per second, quantity squared, minus 60 meters per second, quantity squared. And then we basically do a bunch of conversions. So 1 joule per Newton meter. We're dividing by 2, and we're basically just trying to get from meters squared per second squared via newtons back to joules, essentially. So I think I have to go to the next slide. I'll give you guys a minute to write that out. I don't want to go too fast here, but the next slide has the ultimate solution. So what this is going to end up with is the 3348 minus 2250 plus what this value boils down to. Okay.
Really quick, how did the H2 and H1 switch?
Oh, that was just, so all we did was multiply through by a negative.
Okay.
Yeah, that was, so that changed the numerator here as well. The order of those.
Thanks.
Yep. Yeah, sorry. I think my pacing's a little bit better with you guys when I write all this out. So my apologies for forgetting my writing tablet today. I don't want to zoom through this too fast. Anybody still writing? Okay. So then what this ends up with though, take a look at this. 3348 minus 2550. So that was the enthalpies in and out, in and out respectively. And then all of that velocity difference only gave us a change of 1.35 kilojoules per kilogram, pardon me. So kilojoules per kilogram, they're all the same units, and the change in velocity did very little to the overall energy. When we put this all together, this is our output that comes from basically the turbine in this case. So we have pulled out 797 kilojoules per kilogram of steam that goes through this turbine. All right. So we still have, almost 3350 going in and 2550 coming out. We have this small change with respect to the velocity, but 797 is what we're removing from this system to create energy of some kind, right? To maybe create electricity, whatever we're going to do with that turbine. All right. Okay. I don't think I have enough time to finish the next problem before the top of the hour, so I'm going to jump ahead to the participation problem, and then on Thursday, the first thing I'll do is start with this fourth problem that we didn't get to and work through it in class, and then we'll get into dimensional analysis. And again, I'll get those notes posted this afternoon for Thursday. Okay. Sorry, little preview. Okay, water flows through a pump. The inlet and the outlet are the same diameter and at the same elevation, so we expect their velocities to be the same, their elevations to be the same. If the flow rate remains the same and the pressure difference between the inlet and outlet increases by 3 times, the pump power increases by the square root of 3 times, increases by 2 times, increases by 3 times, increases by 9 times. So think about that. Let me get this going. I'll give you guys a minute, maybe a minute 15 to think through this a little bit. If we write out the equation, I don't have it ready to pop up here, but essentially what we're just looking for is how is power related, the pump power related to this pressure difference, given that these other things are equal. For anybody who's keeping up on current events, apparently there's going to be a big announcement in the next hour. So, all right, we're up to 80, 81. Let's see where we stand. Okay, we'll wait till minute 15. We shouldn't have too many more. Anybody else? Okay, let's take a look here. All right, so we've got 8 of you that chose A, 6 of you chose B, majority overwhelmingly chose C, and 13 of you chose D. The answer indeed is C, and the reason is that if we cancel all those things out on the left-hand side, we're really looking at a linear change of the pressure difference with pump power, right? Those are linearly correlated simply because, they're simply because all the other things go away. There's no other factors that are involved here. And so indeed, the right answer is an increase of 3 times because of change in the pressure difference between inlet and outlet increases by 3 times. Okay, excellent. Thank you for that. Let me get rid of this. And then last thing we'll do here is just remind you that we will have class on Friday. Homework 11 is Thursday. We'll have class on Thursday. Homework 11 is due before class on Thursday. Both Emma and I will hold office hours tomorrow at our usual times, and I'm happy to answer any questions for the next couple minutes if anybody has them. But otherwise, have a great week, and we'll see you on Thursday. Take care.
Thank you.
You bet. Thank you.
Thank you.
Thank you.